Good morning, Los Alamitos. All right, let's continue talking about static electricity. What we learned before is that inside the atom there are protons, which have a positive charge, and electrons, which have a negative electric charge. We also learned that the electrons are mobile, and they're on the outside of the atom, so they're knocked off easily. And the migration of electrons is really what creates static electricity. So all matter, let's change, is electrically neutral, which means equal positive and negative charges, equal protons and electrons. And then if electrons migrate, too many electrons gives that body a negative charge. And of course, too few electrons gives that body a positive charge. So when an object, a body, a thing, is negatively charged, it has too many electrons in it, and it's looking to get rid of them. It's looking to get back to being neutral again. And when it has too few electrons, it's positively charged. So we're just going to call objects that are charged positively positive charges. Okay, we don't need to talk about the microscopic end of things that it means a deficit of electrons. We can just say, hey, that's a positively charged car, or that's a positively charged balloon, or something like that. And that brings up some interesting stuff. First of all, what kinds of materials are there that can do this electrical thing? And when electricity is concerned, the materials fall into two main categories: conductors and insulators. And some of you may have heard the term semiconductor or superconductor. And yes, these are materials that have very odd and interesting properties. But for the most part, things can be broken down into conductors and insulators. Conductors mostly include things that are, oh geez, made of metals. Metals are very good conductors. By the way, not only good conductors of electrons, but also very good conductors of heat, usually. So that's interesting. I wonder if those properties are related. But liquids, such as water, that have ions in them, they can be very good conductors as well. Actually, if you go to chemistry class, they'll tell you that water itself is not a good conductor of electricity, but it's the impurities and the ions and things that are in the water that conduct electricity. So Gatorade, with its electrolytes, its special ions of potassium and I don't know what else they put in there, which are intended for your body to use for something, make Gatorade a very good conductor of electricity. Insulators are things like glass is a very good insulator, ceramic, which I guess a lot of people think of as being glass, or plastics. These are good insulators because in them, the electrons tend to be stuck with whatever atom they are part of. It's really hard to knock electrons free of their atoms. Metals are a particular interesting category. If you've been to chemistry class, you may have heard of metallic bonding. And the idea is that in a metal, all the ions, all the nuclei, I guess, with most of their electrons intact, they form kind of a rigid structure, and then the remaining outer electrons are kind of free to be shared everywhere, like some sort of hippie free love commune kind of thing. And so those electrons can flow very easily. You can get electricity to do things with both of these materials. It's not just conductors that are electrically active. Insulators are electrically active as well, and you know that because of the balloon trick. Right? You rub a balloon on your hair. The balloon is made of latex rubber. I mean, I think they're still making it out of latex rubber. Anyway, it's an insulator, but the area that you rub on your head does something. And although that charge that you created in that area doesn't move around to the rest of the balloon, it's only the part of the balloon that you rubbed in your hair that will stick to the wall. there is still something going on there. So insulators are not immune to electricity, but we certainly sometimes use them in that way. Um, so what we should say here is that conductors allow free flow of I'm going to say charge, okay? We're not going to be specific about its electrons that are flowing, just free flow of charge. By the way, the reason I'm doing that, a lot of this electrical stuff was actually worked out before people knew about the atomic theory of matter and before people knew about the electron. And insulators, charge is kind of stuck in one place, okay? Um, let's see, what can we do here? When you read your book, there are some great drawings of how polar molecules can help you understand this. Let's put let me put that down here. Look at the polarized molecules, polar or polarized. Okay, and a term that's used here is the electron sea. In other words, they think of it as an ocean of electrons, free electrons for everybody, which is why you get shocked by that doorknob, even though maybe the doorknob's not connected to the Earth. Okay, so now that we know that when objects have too many or too few electrons, this is a key area right here. In fact, let's put a big old star next to it. Oh, great looking star, Harmon. Fix that up. Now that we know that that's how things become charged or become charges, the question is how much charge do you need? When you're shuffling your sock-clad feet on the carpet, at what point are you in danger of getting a noticeable shock? And the person who did a lot of research on this is a guy by the name of Charles Augustin Coulomb. When I first saw that name, I thought it was pronounced Coulomb, which is a really fun thing to say. It kind of resonates in the nasal cavity, but it's Coulomb, and he was a French researcher. You know, the science research went through various phases. You know, in the ancient times, Italy was the hotbed of science, and then it went through France. France became like really about the time of the steam engine and all. France was like the scientific powerhouse, and then of course it kind of settled in England in Victorian times, and the Royal Institution of Science in England became the thing. And of course, by the time America is getting into, say, World War I, or let's say the turn of the century, 1900s, lots of Europeans are migrating to America, and America becomes a very serious scientific powerhouse because we established these corporate laboratories to research science in order to try to make new products and stuff. And that was kick-started, especially in this area, by the World War II and the aerospace industry that grew up here in Southern California after World War II. But back to Charles Augustin Coulomb. He was trying to come up with a standard. He was trying to measure the strength of attraction between two things that might have been charged. So he had to come up with a standard of how much charge is going to be 1 unit of charge. And so he defined 1 unit of charge to be 1 Coulomb of charge. Well, maybe he didn't name it after himself, but they did name it after him later. And a Coulomb, let's put this in brackets because it's a unit, is often abbreviated just with the capital C. Now that could be a little problematic. Coulomb of charge, you might think, well, that's degrees Celsius. No, it doesn't have the degree symbol. It's a capital C. Oh, but wait a second, that's a specific heat. No, it's after a number. So a capital C after a number is a Coulomb of charge. 1 Coulomb of charge. And in order to get 1 Coulomb of charge, he worked out that was this many electrons missing or added. Okay, let's take a look at this number. 6, yeah, 0.25, who cares? Times 10 to the 18. Ooh, 18. At least that's divisible by 3. That means it's one of these illions. Okay, 10 to the 6 is a million. 10 to the 9 is a billion. 10 to the 12 is a trillion. 10 to the 15 is a quadrillion. So this is 6 quintillion electrons. That's how many electrons you have to move away from something before you get a charge of 1 Coulomb. And a charge of 1 Coulomb will create a spark that will make you say, ouch. Okay, it's not very scientific at first, but that's really where people were doing this. You got to remember, our founding father Ben Franklin was an electrical researcher of some renown. We'll talk about the kite experiment later, but in those days when they made static electricity, they made some sort of machine or whatever. If they touched it with their finger and it made them say "ouch," they said, "Oh, that's strong. That's strong enough for this." You don't want it too much stronger. You don't want it to say harm you or burn you. Although I guess Ben Franklin did shock himself at one time to the point where he felt burnt. Um, so Charles Augustine Coulomb took this standard of ow and he put a number to it. That's how many electrons. And uh, what we usually do nowadays is we turn this around and we say that 1 Coulomb of electricity. I'm sorry, I already did that. Let's do the other way. That 1 electron has a charge of 1.6 times 10 to the minus 19 coulombs. That's the inverse of this number, 1 over that number. So 1 electron. And this charge on 1 electron has a special symbol. The symbol for charge is a lowercase q, and q with a subscript e is the charge on 1 electron. So the charge on 1 electron is 1.6 times 10 to the minus 19 coulombs. And that's an important enough thing that we're going to put a box around it. We also just let the cat out of the bag, get the symbol for charge, how much charge something has, how many too few or too many electrons is a lowercase q. So now we know charge has the symbol q and is measured in units of coulombs, which are abbreviated with an uppercase C. All right. There's one or two more things we need to talk about in this chapter. We need to talk about Coulomb's law. He actually figured out the force law between charged objects with a very interesting experiment that I will detail later. We also need to talk about Robert Millikan. And yes, that same Robert Millikan that the high school is named after in Long Beach. When he was a researcher in Chicago, he did a very famous experiment to determine the charge on 1 electron. You see, Coulomb proposed this standard, but he didn't actually measure this number. This number was measured by Robert Millikan. And then at the very end of this chapter, we're going to introduce a concept called the electric field. So that's where we're headed. But today, you learned that being charged is having too many or too few electrons. You learned that there are conductor materials that allow the free flow of charge throughout them, and insulating materials where they do allow some amount of charging, but it doesn't flow. It stays in one place. You also learned that a standard unit of charging is the Coulomb, and the Coulomb seat of the pants is enough to discharge into your body and make you go ow, but is really a deficit or excess of this many electrons. And we generally turn this over on its head and talk about the charge on 1 electron being this many coulombs. All right, thank you for your patience.